Hey folks, this is Kevin Jones here to give you the last sort of summary lesson on memory mapped inputs and outputs. Today we are going to sort of reevaluate how the LC3 is able to interact with I/O devices, including memory map registers, synchronization, and interrupts. And at the end we'll show you a couple of different ways we can interact with our hardware, either using polling or using interrupts. So we'll start to get a feel for writing some very short interrupt service routines for our two hardware devices. All right, let's get started. By way of a recap, we can see the LC3 kind of here on the left, and this concept of our memory mapped input here, where I've got 4 memory locations that interact with my keyboard and my display. I've got a keyboard status register, a keyboard data register, a display status register, and a display data register. And these are set up so that the keyboard data register is effectively connected directly to my keyboard, and such that whenever a user presses a key on the keyboard, this register displays the ASCII value of that key that was pressed. And kind of similarly, the display data register is set up so that any value written or any ASCII value written to the display data register will show up on the display. And then both devices have a status register, which gives us 2 very useful pieces of information in the most significant bit. So the keyboard status register has this new bit that alerts us to when new data is written to this register. The display status register has a ready bit that lets us know when the display has read this value and the display data register is ready to receive new information. And then based on what we just learned a few lessons ago about interrupts, both of the status registers have an interrupt enabled bits to potentially allow these devices to interrupt the processor when there's new data in the keyboard, or potentially when the display data register is empty and it's ready to receive new information. And just like we saw in our lessons on the memory mapped inputs and outputs, the way we do that in the actual implementation is that we have this piece of address control logic that sort of interfaces between our actual instruction data memory and these registers. The data registers of which are connected to the actual hardware devices. And the address control logic is set up so that when the processor reads or writes to one of these 4 registers, it's able to configure the INMUX or these registers so that performing reads and writes from these addresses effectively controls these 4 registers. And then when we started talking about interrupts, we added a little piece of logic to that so that the keyboards and the data registers the keyboards and the displays can potentially interrupt our processor. So the status bit, the most significant bit position, and the interrupt enable are ANDed together and then sent to this encoder. So as long as the device is, if there's for the keyboard, as long as there's new data that's ready to be written and the device is allowed to interrupt the processor, then we've met 2 of our 4 conditions. That goes to the encoder. As long as the keyboard is the highest priority interrupt that needs servicing, and that value is higher than the current priority level of the task that's running on the processor at the time, then we've met criteria 3, where this service routine is more important than what we're running at the time. And then as long as number 4, lastly, the global interrupts are enabled, then we send this signal to our processor that allows the interrupts to occur. So that's kind of like a 30,000 foot view of our memory mapped I/O. And then there are really 2 ways we can kind of interact with these hardware devices. So the first way, the way that came the most naturally was polling. Which kind of comes in 2 flavors. We could do this thing where we just periodically check something like the keyboard status register to see if there's new information. So in this code example, I'm going to check if there's new information. If there's not, then I do other stuff, and eventually I branch back up to the top and check again. And at some point when I make this check at the top of my loop, if there's new data, then I load that value from the data register into R0 and I do something with it. The other kind of way is something called a busy waiting, where I'm literally spinning, waiting for new data in the keyboard data register, and as soon as there is, then I get to do something with it, and maybe other code runs, and eventually I come back to the top of this loop, and I just spin here, kind of waiting for new data to come in on the keyboard. I'll say at this point that, to sort of set up for the reason why interrupts were important, I was very quick to point out how these two means of reading from our hardware have downsides, which are, kind of both cases. There's a possibility that we miss data coming in from the keyboard if we're not able to read the keyboard data register quickly enough, or we sort of are blocking other codes from running on the processor while we're waiting for new data to come in on the keyboard. And those are definitely downsides to this technique. The one upside that I will give polling is that it's much simpler than when we move to interrupts. For certain applications that where it's not necessarily strictly important that keyboard data be responded to immediately, sometimes polling can be the better way to go, since it's just simpler. But if we assume that we're writing software and it's very important to us that we sort of be able to multitask, or that we respond to keyboard data immediately, then we can use our interrupts here to be able to do that. So this is a very simple program where I've got the keyboard ISR at memory location hex 500, and we'll assume this note here says we'll assume that 500 has been loaded into a memory location 0180. Recall that this is the location of the keyboard vector. This is the location in the interrupt vector table where we get the starting address of our keyboard service routine. So in this sort of small example, what we're going to do is, once we're in this ISR, we know that there's new data in the keyboard, so we're going to load that into R1. We'll wait here until the display status register tells us that the data register is ready to receive more data, and then we'll store whatever value is just typed on the keyboard into the display data register to send that out to the display. So this is just a routine that sort of echoes whatever character was typed at the keyboard. And then we end with our RTI instruction. So this is a little ISR that does that sort of echoing of the characters. Anything typed shows up on the display. And down here in my main program, the user program starting at location 3000, in this example, there's nothing else that I want this thing to do. I can just sort of spin here in this loop forever. And this is just to kind of show that I could be doing anything. I'm doing nothing. But when the processor is sending characters to the display, it's doing all that inside the interrupt service routine. And if I wanted to, I could do something else in my main program. So this is one kind of simple interrupt service routine. We'll look at some more complicated ones in the next two lessons. But just to sort of recap, this is kind of the 30,000 foot view, like I said, of our interfacing with memory. Our interfacing with our hardware devices in a way that allows us to use normal loads and stores to talk to these hardware devices and to potentially enable these interrupts. All right, that's all I got. I'll see you next time.